Hi, so I want to talk to you about implicit differentiation, which is a concept that I didn't quite understand when I was in high school, but none of the sort of test questions really brought out that misunderstanding. So I was able to get all the marks in implicit differentiation without actually knowing the concept properly. And I want to sort of show you um, what I've learned since then and how some of the other explanations for implicit differentiation isn't complete or not quite correct. Okay. So what is implicit differentiation? So it's when you're given like an equation like this, so I'll do it through this example. You're asked to find the derivative of dy dx. Okay. And so what you're told to do, okay, is to differentiate both sides. Okay. So it's an equation, you can do the same thing to both sides, right? Okay. And so what you do is with respect to x, okay, and what happens is the x squared becomes 2x. Okay. Now, what does the y squared become? We'll leave that for now, and then the 1 becomes a 0. Okay, so the y squared, you're told by the chain rule, right? So you bring the 2 down, and you differentiate the y squared as if it was just x squared. Okay, but then to account for the fact that y isn't just x, you need to use the chain rule and times it by the derivative of x. Okay. And so now you have an equation that has dy dx in it. Okay, and you make dy dx the subject. So you put minus 2x on the other side, and you divide by 2y. So dy dx equals minus x over y. Okay, and so maybe as an exercise, you can try to think about what's wrong with what we just did. Is everything we did completely legit? Okay, and so when I was in school, I didn't really think too much about it, and um, and this would get you all the marks you needed in the exams, and it would seem like you understood the concept. Okay, but I later discovered I was wondering why, like, why is this first of all called implicit differentiation when all it seems to be doing is differentiating both sides with respect to x? You know, so if you have an equation, you can differentiate both sides with respect to x. So why does the word implicit even come into it? Why isn't it just differentiation? We're just differentiating both sides instead of having sort of um, f of x equals something and then just differentiating one side. Okay, well, I guess so. There's a couple of things that we want to explain. So when differentiating, okay, you're taught that differentiation is something that you do to functions, okay, and well, we just did it too. So we actually have a circle. So x squared plus y squared is a circle equals 1, and a circle isn't a function, okay, and so if it isn't a function, then how is it that we're allowed to differentiate the y? Okay, and then the answer is um, that even though it's not a function, because if you have a vertical line, it'll hit the graph twice. It's locally a function. So if you zoom in here, it's a function. So it still makes sense to talk about the derivative. So the derivative is actually a local property. So the word implicit really takes care of the fact that it's not really a function, but you can still get the derivative anyway by sort of pretending it is a function. Okay, so there's actually a lot more that needs to be justified than just differentiating both sides. Okay, and then obviously the high school stuff that you might not you might have to realize that y cannot be 0 here as well. So it's not quite defined but that's more a minor thing. Yeah, so this was interesting because I never really understood it, and I was like, surely other people didn't understand this either, and it turned out to be the case that um, basically everyone I knew didn't understand this. But then some people, when I showed them this, they changed their mind and like, oh wow, that's what it's really about. And some people actually they were stubborn and they just refused to believe that was the reason that this is implicit differentiation. So even my friend who went to MIT for grad school, like he just differentiated both sides without thinking too much about it. And then I told him, and he's like, "Oh wow, it actually is implicit function theorem." Okay, and so whereas some other guy I met just could not accept it. He actually insisted that y actually is a function. So um and actually this reminds me. So I guess um maybe this is worth talking about. We're getting a little bit off topic, but I think as far as implicit differentiation is concerned, our discussion is over. But I thought this was kind of interesting because this reminds me of something that happened in the classroom when I was in high school. Okay, so the point is, even though x squared plus y squared equals 1 is not a function, you can actually create the semicircle functions by taking the square root, right? So you write it as y is plus or minus the square root of 1 minus x squared. Okay, and so you do get like a function y equals root 1 minus x squared, and you get another function y equals minus root 1 minus x squared, and these correspond to, so the first one is the top semicircle, and the second one is the bottom semicircle. Okay, and so he kept convincing me that, trying to convince me that these were the actual functions we're talking about, and we're finding the derivative of those. Um, which is to some extent true because the derivative of those functions are equal to the derivative of the derivative you're looking for. Okay, but the point is, um, so um, yeah, so uh, I guess so the functions that you get, um, so yeah, so I mean you you do have to make a choice, and also it's not really the most natural way to get a function. I mean, of course, these are the only options if you want the function to be differentiable and continuous. But um, on another note, in the school when the teacher was presenting this, I remember that he said, yeah, so the circle is not a function, and we get this plus or minus thing, and we have these two functions. And at the time, I was like, well, why does the plus and minus have to be consistent throughout the function, right? Why does it have to be that it's always plus? Why can't it be like plus sometimes and minus other times? Okay, so in some sense you could have like a function where it is so many points that are above and so many points are below. It almost looks like a circle anyway, but it never has 2 points on any given line. So kind of like I was just thinking like it was like some sort of like a circle looking thing that was actually a function. Okay, and then I mentioned this to my teacher, but I guess that was maybe like year 10 or something. I guess because or year 9, because maybe I had a bit of a reputation for being like a class clown. I don't know how I got that reputation, but he just dismissed my ideas as just trolling or something. So he's like, Michael, stop being an idiot. And then I was like, oh, okay, maybe I was actually just being an idiot. So then I just kind of never thought about it again. And then obviously later on, he realized this is kind of, it even has like a name when you're doing like functional equations. It's called the pointwise trap, right? Or the pointwise fallacy, where you assume that sort of when you solve the function for one point of y, it has to be true for all the points y, right? So like the consistent plus sign. So actually you can have lots of different functions, and even if you think, well, you can't have them continuous, I mean, differentiable, but you can kind of have it like even in pieces. So you could have like a piece here, and then a piece here, and a piece there, and then a piece there. And um, so there's actually a lot of choices for functions, and in these cases the derivatives make sense too. It's kind of convenient that they're all the same when it's defined. Okay. Yeah, so I guess that was a little bit of a nostalgic moment in the maths class, and I don't know, it was kind of very discouraging in hindsight. At the time I didn't really realize it. Okay, so I hope you understood implicit differentiation.